So now we are starting with the new chapter, that is your nanochemistry. So we are starting is with our nanochemistry. So what is the meant by this term, that is your nano stands for? So nano something basically means, from the name try to recognize it. So nano basically means something that is small in size, right? So it is small in the size. So basically in the nanochemistry what we study is the study of these small particles. So how much small and what actually these means, so that what are their properties, how is it differentiating from the bulk materials, their preparation methods, their characterization, all that things about these small particles we are gonna cover in this particular unit. Okay, so let us begin this. So the word nanomaterials, basically it is derived from a Greek word which means the nanos, and the word nanos, it means to be dwarf in the nature. So dwarf refers to something that is small in size. Okay, so now what we are seeing, that it is small in size, but how much small, that is not mentioned, because something in a particular dimension when we categorize it, then we can say that this particular molecules or the particles are gonna fall in the category of the nanoparticles, right? So what is the size of these nanomaterials? Basically it lies in the range of 1 to 100 nanometers range. So if you have particles which is lying in their radius or their diameters is falling in this particular range, we can say these are my nanoparticles. So now what is this nanometer terms? So basically 1 nanometer, it is equal to your 10 raised to the power of minus of 9 meters of it. And we know that 1 meter is equal to the 100 centimeter of it. So 1 nanometer in the centimeter, you can write it as 10 raised to the power of minus of 9, and 1 meter is 10 raised to the power of 2 in the centimeter. So this becomes my 10 raised to the power of minus of the 7 centimeter of it. So this is the dimensions of basically a nanoparticle. That is, this range, it is important that it lies in between 1 to 100 nanometers, and nanometers in the meters you can also write it, and in the case of the centimeter also you can use this relationships for that. Okay, so this is how we say that if a particular material is falling in this particular range, that is gonna be my nanomaterial. So what we have learned is that in the chemistry we say that atoms or the molecules are the smallest particles. So how do we say that a particular species is an atom or a molecule, and how do they form the nanomaterials? So basically if you have number of the atoms or the molecules, that is a particular species, you will be calling it an atom or a molecule if you have 1 to 10 atoms are present in it. Like the sulfur 8 molecule if I consider. So here what happens is there are 8 atoms of the sulfur are present in your S8 molecule. So S8 basically falls in the category of the atoms or the molecules we are seeing. That is basically the smallest unit of the any matter we are having, right? Now next category that is higher than this we have is the nanomaterials. And in the nanomaterials, basically these are formed when we combine these atoms or the molecules. Now how many atoms or molecules are gonna combine? That is when you have 10 to 10 raised to the power of the 6 number of the atoms they have combined together. So this is gonna form your nanoparticles. Okay, and their sizes is will be lying in this particular range, right? And if you have something in which there is more than 10 raised to the power of 6 atoms are present, then that particular matter is falls under the category of your bulk material. So this is how, on the basis of the number of the atoms or a molecules present in a particular matter species, we classify them as the smallest unit, that is your atoms or the molecules. Combining them we get your nanomaterials, and further combining that clusters that have been formed will give you the bulk material, right? So now what we are focusing is upon this nanomaterials range, which is formed from the atoms or the molecules, or from the bulk material also you can form. In the preparation method, I'll be telling how both of these will be useful for the generation. Okay, so this much I hope it is clear. The basic one we have said, that what is the size of these nanomaterials and how do we characterize them. Right, now comes the nanomaterials. So we have seen that the sizes, we can say that it is gonna fall in the 1 to 100 nanometers range. We are gonna have the size of the nanoparticles. But what actually is the nanomaterials? So basically we have three different dimensions in which we describe the size of any particular species, right? So suppose this is my pen, or you can consider that a cubic box you are having. So for a cubic box, suppose this is the one, or a cube or a cuboid you can consider. So any of them. So this is basically a species I'm having. Now to describe the shape of this, basically the size of it, that is to tell its volume, its surface area, I need is the length of it, I need is the breadth of this particular species, and we need is the height of it. And these three, length, breadth and height, we are having in the three different dimensions. Suppose your length is going in this x direction, this height is going in the z direction, you can say, and this is going in the, basically this is the y direction. So basically breadth we are having is in the y axis we are having. That means to define the basically the dimensions of any species, we need is the three of the x's, help x, y and the z. And in the nanomaterials, how do we say that if you have a particular material in which one, at least one or more than one of these x's, they lie in the nanoscale region, that type of the materials are called as your nanomaterials. So basically what we are saying, the materials, the material in which any one or more than one axis lies in the nanoscale region, in the nanoscale range. What is this nanoscale range? That is to the 1 to the 100 nanometers of it. That means either my x-axis, suppose you are having a particular species in which the x-axis range is in the, that is this length we have made it to be in the nanometer range, breadth or height are the normal range, that is a bulk material, basically you can say they are having that particular range. So that then we can say that it is my nanoscale. So one of the x's is made to be falling in the nanoscale region. So we are gonna get is the nanomaterial. Either one or more than one x's are falling in that. So by this, what is gonna happen when you convert the basically the bulk materials to the nanomaterials, when you are shifting? So these type of the materials you are preparing, they possesses a certain unique properties. So the materials in which one or more than one axis they lie in the nanoscale range are your nanomaterials, and these nanomaterials, they have the unique properties. Materials have the unique unique properties. Unique properties. So what are these unique properties? Basically, they have the high volume to this high volume to the surface area ratio they are having is the more in the nature. So they have the high surface to the volume ratio. They have high surface area to the volume ratio you are having is more. Volume ratio. So due to that various properties it changes. So there will be the difference in their electrical properties you will be observing. Their electrical properties changes. Electrical properties, the changes observed. Their magnetic properties, these changes. There will be change in their magnetic properties you will be observing. Properties, their thermal properties changes, their thermal properties, their melting points it changes. So all these characteristic properties of the materials it changes when you shift from the bulk material to the nanoparticle range. Okay, so now let us learn about who is basically the father of these nanoscience and the nanotechnology. So here you are encountering two new words. One is the nanoscience and other is the nanotechnology. I'll be telling you the difference between them. But the father of the nanoscience and the nanotech is your Richard Feynman. You should remember the name of it directly. The questions can be framed in the form of the MCQs in this. So it can be asked who is known as the father of your nanoscience or the nanotechnology. That is your Richard Feynman we are having. And the term nanotechnology, it was given to us by a scientist whose name it was the Mario Taniguchi. So these two names are the important and can be asked in your exams. Okay, so now let us see that we have said that there are various types of the nanomaterials we can have. We can have the, on the basis of the dimensions we can further classify these basically nanomaterials. I have said that the materials in which at least one of the excess range is in the nanoscale, that particular species we call it to be the nanoparticles. So based upon the dimensions we can classify the nanoscale nanoparticles basically as your 0-dimensional, 1-dimensional, 2-dimensional and your 3-dimensional. So what generally we say is that if you are having a 0-dimensional species, it means none of the axis is lying in the region of that particular region, it is not like. But in the case of nanomaterials, it is not like that. It is just the reverse you have to consider. Basically, the 0-dimensional, it refers to the dimensions where all the three axes, basically x-axis, your y-axis and your z-axis, when all of these three, they are lying in the nanoscale region, the particular nanomaterial, it falls into the category of your 0-dimensional species. So I have written the definition of it. So 0 dimension basically refers to the nanomaterials in which all the dimensions, so make sure you are using this, that all the dimensions basically means we are referring to the 3 dimensions, that is your x, y and the z axis we are saying. All of these three are gonna fall in the nanoscale region. Okay, what are the examples of your 0-dimensional nanomaterials? You have the carbon dots, you have the quantum dots, you have the gold nanoparticles, and you have the fullerenes. Fullerene basically is your Buckminster ball that you have when 60 carbon C60 it is called C60. That means 60 carbon atoms they have arranged itself into a ball like structure. Basically it is an allotrope of your carbon you are having. Right, so this is basically the 0-dimensional nanoparticles in which all the 3 dimensions of the particle is lying in the nanoscale region only. Okay, now moving on to the next dimension, that is your one dimension. So start excluding one of the dimensions from here now. So here in the 0 dimension, all the three were lying in the nanoscale region. In the 1 dimensional, one is not lying in the nanoscale region, but the two are lying in the nanoscale region. Let's try to remove one of them, that we are moving from the 0 to the 1 dimensional. So in the nanomaterials in which 1 dimension, it is not in the nanoscale range, that is called as my 1-dimensional nanoparticles. 0-dimensional, all of these three. 1-dimensional, one is not lying and two are lying in the nanoscale region. Examples are important, that is your carbon quantum wires that you have and the carbon nanotubes. These fall in the category of your 1-dimensional. These will be having, suppose your x and y axis is lying in the nanoscale region, but one of the axis, that is your z axis, is not lying in the nanoscale region. This results into the formation of your quantum wires. Okay, now next is about the 2-dimensionals. Now as we move from the 0 to the 1, then 1 to the 2. So in the one of the axis was not lying in the nanoscale region. Now in the 2 dimensions, two of the dimensions will be not lying in the nanoscale region. So here now you have nanomaterials in which two dimensions are out of the nanoscale range. That means they are not lying in the nanoscale range. Only one dimension is lying in the nanoscale range. So the examples you have, that is your graphene, you have the thin films and the nanosheets. So these fall in the category of the two-dimensional molecules. Okay, two-dimensional nanoparticles. Next is about the three-dimension. That means basically these are the bulk materials but have the small particles, that is they are lying in the nanoscale region, but all the three dimensions are not in the falling in the nanoscale range. Examples for this, that is your allotropes of the carbon, that is your diamond, graphite and the nanostructured bulk materials that you have it. So this is the first classification of the nanomaterials that we can have on the basis of the dimensions. We can have the 0 dimension, 1 dimension, 2 and the 3 dimensions. Okay, so you have to pay attention that here generally we say that a particular species is lying in the 0 dimension or it is in the 1 dimension. So we expect that many number of the excess should be lying in the nanoscale region, but in actual it is the reverse. In the 0 dimensions all the three are falling in the nanoscale region. Then as you move further, try to exclude one of the excesses not lying in the nanoscale region and further the classifications are made. As I said, these examples are important. Directly it will be framed in the form of the match the columns. These questions can be asked. Okay. Now the next classification of the nanomaterials that we can have is that is on the basis of their composition, that is the material of which my nanomaterials have been made of. So the first is your carbon based nanoparticles. So carbon basically means that the species is that the nanomaterials that I am having will be made up of the carbon molecules or the carbon atoms we are having, right? So this is that is made up of the material that is made up of the carbon atoms. Example is, we have already seen, you were having the fullerenes that was falling in fullerene, that is your Buckminster ball that you have. It falls in the category of my zero dimensional nanoparticles, right? Next we have seen is about the nanotubes. We have seen about the graphenes. Graphene, it was lying in my two-dimensional nanoparticles. So all these three are made up of the carbon atoms and they are falling in the nanoscale ranges. So that is why these are my nanomaterials and are made up of the carbon. So these are my carbon based nanoparticles. Okay. Now next is you can have is that is made up of the metal based. So basically second one is your metal based nanomaterials. The nanomaterials which are basically made up of the metals or the metal oxides, right? Examples is you can have the titanium oxide, you can have the silver nanoparticles. So basically titanium oxide that you have, it is used in your photovoltaic cells, it is being used, and the silver nanoparticles is used basically in the purification of the water. So these are the metals and the metal oxides, the species these are made up of, and that is these are your metal based nanomaterials. Alright. Next is we have the polymeric nanomaterials. Basically the polymers are used to make the nanomaterials, that is it is formed by combining two or more of the materials to achieve the unique properties. Unique properties will be the electrical properties are different as compared to the bulk material. So when these two or more of these species they are combining and the polymeric chain is getting being formed, it is falling in the nanomaterials range and these are gonna possess the unique properties. Examples of it are the dendrimers and the polymer nano composite. So these are my polymeric nanomaterials. Right. Next one we can have is the composite nanomaterials. Composite basically means it is formed by combining two or more of the materials so that we can have the unique properties. Example you can say the nano clays that you have. So nanoclays will be lying in the region that is of the nanoscale range. You will be having their sizes, but these are formed by the combination of the two or more of the materials, and that particular species which you have formed is gonna possess the unique properties. So it is my composite nanomaterials. So this was about the classification of the various nanomaterials. So far we have discussed about the basic portion of the nanomaterials, that what is gonna be the size of it, who is the father of the nanotechnology or the nanoscience, how was this term, it was by who, by which scientist it was being given to us, and then this classification we have seen on the basis of the dimensions, also on the basis of the materials of which the nanoparticles are being made. So now, as I said, you have encountered two of the words. One is your nanoscience and other is the nanotechnology. So what is basically the difference between these two terms? Let us try to find it out now. So nanoscience, basically it refers to the branch of the science which is used to make in which we study basically about these nanoparticles. We study about these nanoparticles, their physical, their properties, basically we are studying. That branch, it falls in the category of the nanoscience. And whereas the nanotechnology refers to the branch in which we study about the application of these nanoparticles that we have produced. So nanoscience basically refers to the branch in which we study about the nanoparticles, in which we study about these nanoparticles and their properties, and also we include the related phenomena. Also we study about their related phenomena, their related phenomena. Whereas in the nanotechnology, we are gonna use is, that is basically the study of the application part of these nanomaterials. So this basically includes the study of the application of the nanomaterials. So we have seen through an example, you will be getting the more clarity over it. So we have said that the quantum dots are my nanomaterials. So this is what I have said. So basically we have said that my quantum dots are my nanomaterials, and these nanomaterials, about their properties, their preparation methods, all this study about these quantum dots we will be studying under the branch that is my nanoscience. And if I want to see the application of it, basically these nanomaterials are used in the led screens, tv screens that we are having. So they are small particles, it is made up of that, and that is the nanomaterials. So this basically becomes the application part of the nanomaterials in the LED TV screens that we are having. So this is studied under the nanotechnology. So I hope the difference between the two is clear. So we are to study about the quantum dots, its physical properties, basically about its properties, that is it, you can say the what is the color of it, right? So what is its electrical conductivity, what is its electrical conductivity, what is its melting point and wettability, all these properties, that is basically about the quantum dots we are studying in the nanoscience. And the application of it, example is in the LED TV screens, this is being used. LED TV screens, these are made up of the quantum dots. So this is the difference between the nanoscience and the nanotechnology. Okay, so I hope the difference between the two is clear now. So now let us move upon to the next topic of the nanomaterials, that is basically we are going to learn about the properties. So we have said that as we are moving from the bulk material to the nano size particles, we are moving. So the properties of these materials, it changes. So why is it so that these properties are changing, and how is it gonna vary from the bulk materials? All that things we are gonna look upon now. Okay, so we are gonna learn about the properties of the nanomaterials. So basically we are looking upon to the size dependent properties of the nanoparticles. So in this, the various properties we will be covering. The first one we are gonna look upon is the electrical properties. Electrical properties, that how do these vary when we move from the bulk material to the nanoscale particles. So electrical properties, basically in the solid substances that you can have the conductors, the insulators, and we can have the semiconductors. So their conduction property, it is electrical property, basically means the one that is able to conduct the electricity through it, right? So we can this conduction, it is basically studied in the solid state using the band gap theory. So according to that, what we say is that there exist two type of the bands in the systems we are having, that is in your solid state. We have learned that in the insulators or the conductors, two types of the bands basically it exists. So according to the band gap theory, we have two types of the bands. Bands basically means this large number of the energy levels are present in it. So this in the form of the bands it is present like this. So this is in the form of the bands we are having, right? So the lower band, it is called as my valence band. This is my valence band, and the upper one in which there is a conduction of the electrons, this is known as my conduction band. So this gap we have drawn, that is these gaps we have drawn, this is for the semiconductor systems you are observing. That is between these two levels, that is your valence band and the conduction band, some of the gap is present. This gap is known as the band gap. So this is the band gap that I am having. If you will be looking upon to the solids in this conductor systems, so these overlapping will be there between these two bands. So these are basically lying in between one another. So like this, these are completely overlapping. So this is the conduction band and this is the valence band, and this is in the case of the conductors we have it. Whereas in the insulator, a large energy gap is there between your valence band and the conduction band. So like this, a large gap is present between them. So this is the one. So this gap you can see. So a large number of the levels we are having. So this is the valence band and this is the conduction band, and this is for the insulators we are having. Insulators. So now let us see. We are taking is the example of the semiconductor materials where there is a small energy band gap is present between the valence band and the conduction band. So as we are moving from the bulk properties to the nanoscale, so what happens to these band gaps? Let us observe now. So this is the bulk material you are having, right? So these large number of the energy gaps are present and there is a gap between these two, and this is gonna be in the bulk material. So now as you move from the bulk material to the nanoscale region, so what happens? We are breaking the molecules to the basically smaller ones. So due to that, these gaps that you are having, it starts changing into the discrete energy level now. So in the bulk materials, large number of the atoms, basically these are present in the close proximity. So due to that, these energy levels, they exist in the form of these bands you are having. But as you shift to the from the bulk to the small particles, basically you are going. So these bands, basically because number of the atoms are now decreasing as you are moving from the bulk to the smaller scale, the number of the atoms are decreasing. So according to that, the number of the energy levels also are gonna decrease. So instead of the bands, now we are gonna have is the discrete energy levels we are having. So we are having like these gaps you will be observing. So this is the instead of the band gaps, instead of the bands, these discrete energy levels now we have start forming like this. So this is the gap now we are observing in this case between these energy levels. Now further, if you decrease the sizes of it, more discrete energy levels you are gonna observe like this. So you can see that here this gap will be present between these energy levels now. So basically from in the bulk, large number of the atoms it was present, due to that the energy levels they did overlapping and you were having the bands you were having. But when you shifted to the smaller particles, that is to the nanomaterials, you are going, so these size of these basically the bands is shifting to the discrete energy level, that is you are shifting to the quantum approach now, right? So this is what is happening as you are shifting. And if you talk about the energy band gaps, and that is about the conductivity, if you see, so here you can see conductivity will take place only when the electron excitation is taking place in the from the valence band to the conduction band. This is in the semiconductors we are observing this. This is for the semiconductors we are observing, and this is as we are moving to the nanoscale region, nanoscale. So the quantum effects basically we are observing, quantum levels we are having now, quantum levels, that is the discrete energy levels we are having, discrete energy levels you are now observing. So here you can see in the case of semiconductors, I was saying that conduction will be taking place, electron transfer from the valence band to the conduction band it is taking. So as you are moving from the bulk to the nanomaterials, basically you can see that this energy gap that I am having. So in the bulk material, this much was my energy band gap. Now as I break it into the smaller ones, so this energy band gap I'm having. Now further if I'm breaking, so more decrease in the energy band gap I'm having, sorry, this discrete energy levels, and the gap between these two energy levels, it is now increasing, right? So this gap has now been increased. So due to that, as the band gap is, as the gap is increasing, so more amount of the energy will be required for the excitation of the electrons from the one energy level to the another energy level. That is, we can say that in the case of the semiconductor materials, as we are going from the bulk to the nanomaterials, their conductivity it is decreasing because the gap between the energy levels it has now been increased. So we can say that in the case of semiconductors, the electrical conductivity, it decreases as we move from move from bulk materials, bulk to the nanomaterials, because the gap between the levels, because the gap between the levels, it increases, it increases, it increases. So this is the scenario you are gonna observe in the case of semiconductors. One is the semiconductor bulk material you are having, and one is the semiconductors nanomaterials you are having. If you try to observe the conductivity of these two, the bulk material is gonna show you the more conductivity. Reason being, here I was having the band gaps, and in that the comparatively less energy band gap it is there. So electrons excitation is easily possible. But as I shifted from the this bulk materials to the nanoparticles, now the levels instead of the bands, now the number of the atoms since they are less, so the bands it has now changed to the discrete energy levels, basically to the quantum levels we have now shifted. And due to that, this we are during this process we are observing that the gap between the energy levels it has now been increased. So due to that, what you will be observing in the case of the semiconductors, your electrical conductivity it is gonna decrease in the case of the nanomaterials. Now what happens in the metals? So metals basically are your good conductors of the electricity. So this type of the scenario it is there, that is of the conductors. So overlap is there between the valence band and the conduction band. As you will be shifting from the conductor band in the case of the conductors, from the bulk material to the nano material, basically you will be going. So there still conduction it is gonna be there. In fact, there will be increase in the conduction, because in the conduction band already the electron presence we are having, right? So we can say in case of the metals, or you can say in case of the conductors we are observing, the electrical conductivity it is increased. Electrical conductivity, it increases as we go from bulk material to the nanoparticles. So this is the scenario of the electrical properties. How do they change when you are shifting from the bulk material to the nanomaterial? The change in the properties is the reason lies between these facts. From the band gaps, now you are going to the quantum levels. Okay, so this was your first properties, that is dependent upon the size, which was my electrical properties. That is basically the conduction is affected when you are going from the bulk materials to the nanomaterials. Okay, now the next property we are gonna look upon is their optical properties. Optical properties. So optical properties basically refers to the colors of these materials, right? So if you talk about this thing, so if you have suppose the gold material, if you are having the gold, I am taking it into the bulk material, that is gonna have the yellow color it possesses. But as you shift to the this nanomaterials, this change in the color also you are observing. It gold nanoparticles, basically they are having the red color. So these sometimes they are called as the red souls, or the red color they are possessing, whereas the bulk material, if you are seeing, it is possessing the yellow color. Now why is it so? Again the same reason it is there, because you can see the optical properties is because of the absorption of the light, right? Because anything is gonna deflect the color. This pen, I'm saying it is black in the color, or anything around you is a colored material, that is dependent upon the absorption of the light, that is dependent upon the band gaps that you are having. So now what is going to happen? The absorption of the light and the emission is responsible basically for the optical properties. Emission is responsible for the color of any substance, any substance you are seeing, because anything that is colored, the light is getting being absorbed, it goes from the lower energy level to the higher energy level, and when it comes back to the ground state, it is gonna emit the light of the particular radiation that is visible to you. So that basically is the color of, that is basically representing the color of that particular species. Now what is happening? We are going from the bulk materials, this is the bulk material, in that these type of the band gaps I'm having, these bands we are having. So as you go, these energy levels it is changing. That is, suppose the bulk material I was having, suppose this is the material I'm having, I'm breaking it. So initially I break it into the half. So due to that, what is going to happen? The number of the atoms, suppose this is the material we are having, and in this, the on halving it, the number of the atoms in it will be also decreased. So due to that, the number of the band gaps, they will be changing to these type of the energy levels now. Now further, if I break this particular, further if I am breaking this half molecule, half species that I was having, now further breaking of it I am doing it. So again what is going to happen? These energy gaps, it is the energy levels, it will be again changing. Discrete energy levels we are going, and further again if you move, so again this some changes in this energy levels it is being observed. So basically these energy levels, they are dynamic in the nature, not a fixed energy gap we are having. As we are decreasing, as we are changing the size of this particular species from the bulk to the nanoscale, during that process when we are going, So basically we can say that suppose in along this axis I have broken this. So some type of the change in the energy band gaps you will be observing. Then along the different axis if you are breaking. So based upon that the different dimensionality you will be having in the nanomaterials. So main thing is we are producing the different types of the nanomaterials now. So during that process these energy levels it changes. Due to that these energy levels now they are dynamic in the nature. Right, so due to that there is a difference between the gap that is present, and corresponding to this gap that we are having the light energy will be observed by the particles. Like in the ground state suppose these are present, this is gonna go to the excited level and will be coming back. So different band gap, different gaps is now being there. So corresponding to that different light absorption will be there of the different wavelengths, and the complementary color will be also the different one. So this is what is happening. So we can say here is that because these are because the dynamic energy levels we are now having, dynamic energy levels, which means that the fixed energy gap it is not there. Due to the because of the dynamic energy levels, the color of the materials, it changes. Color of the material it changes as the wavelength of the light observed is dependent upon the energy band gap, is dependent on the energy band energy band gap. Example, if you see, that is, example is my gold material. Example is the gold. In the bulk it has the yellow color. In the bulk material it possesses the yellow color, whereas if I am going to the nanomaterials, this is gonna possess the red color in that. That is why it is sometimes called as the red souls I am having. So this is the color, and what is the reason for it? That is going from the bulk to the nanomaterial, the band gap it changes, band gap changes. So the light observed also changes, and correspondingly different colors are obtained, and correspondingly different colors are obtained are obtained. So this is the reason for this. Okay, so this is how the optical properties it changes. That is when we are going from the bulk to the nanomaterials, and the reason lies in between the again the energy band gaps. Right, now the next property we are gonna look upon is the reactivity of these materials. So we are gonna look upon to the chemical reactivity. So if I compare, one is the bulk material and other is the nanomaterial, how is the reactivity gonna vary? So this is the species, suppose I am having, this is bulky material I am having. So now what I do is I break it into these small pieces. I am breaking along the different axes, I am breaking it and bringing it to the nanoscale particles. Right. So what basically happens now, if I want to see the reactivity, that means I will be observing that complete surface in the bulk, it will be available for the reaction to take place. Right, this complete surface, the top surface, the sides, and all these sides will be available for the reaction to take place. Now if I break it into these small pieces, so basically what is gonna happen, your surface area to the volume ratio, it is gonna increase when you are going from the bulk to the nanomaterials. So this is suppose the bulk species. This is my cube, you can consider, or the cuboid, whatsoever. So this is basically the bulk material. Now you have broken it into the small pieces. So small cubes you will be having like this, right? So these basically cubes you can consider, they are lying in the nanoscale region because we are talking about the nanomaterial. So this species we have made it. So from the bulk, small species you are going. So what is gonna happen? Basically, originally this surfaces were available for the reaction to take place. Now you can see more number of the sites will be available for the reaction to take place because more number of the active sites you will be having. So we can say that the chemical reactivity, it is gonna increase as you go from the bulk to the nanomaterials. Reason it lies in the fact that your surface area to the volume ratio, it increases. So you can see that suppose you are having this cube bulk material that I am having. Suppose this is of the length 2 centimeter or the 2 centimeter length, it is gonna have length, breadth and the height. We can say that these all are of the 2 centimeter. If I try to find the, this is 2 centimeter volume of it, that is gonna be the side cube. So we have 2 cube of it and this is gonna be equal to the 8 centimeter cube. Basically we are having the volume of it. And if I try to find the surface area of it, that is gonna be equal to the 6a square of it. So this is gonna be 6 into the a square, that is the 4. So this is gonna be 24. So if I find the ratio of its surface area to the volume ratio, I'm gonna get is 24 by the 8, that is gonna be 3 in number. Right, now in this species, now from this large block we have prepared small cubes. Suppose each cube is of the 1 centimeter I'm having. So here now the cube volume, it is gonna be side cube. So this is gonna be 1 cubic centimeter, right? And if we find the surface area of it, so that is gonna be 6a square. So this is gonna be 6 centimeter square area I'm gonna get it. So if I try to find the ratio of its surface area to the volume ratio, we will be having 6 is to the 1, that is gonna be 6 in number. So you can see as you are going from the bulk to the nanoparticles, the surface area to the volume ratio, it is increasing. In this case it is 3, the ratio is there. Now we are having is 6. So surface area to the volume ratio, it has now been increased. Hence we can say that the chemical reactivity, it also increases when we go from the bulk to the nanomaterial. So this is the bulk, B-U-L-K, as you go from the bulk to the nanoparticles. So this is the reason for that. So we can say is that the surface area to the volume ratio, it increases as we go from bulk to the nanomaterials, hence we can say chemical reactivity, it increases. Chemical reactivity, it increases. So basically more surface area is now available for the reaction to take place on that material. Example you can see is that suppose you have a tablet of the aspirin, okay, and the complete tablet you try to dissolve it into the glass of the water, and on the other side what you do is break that tablet of the aspirin into the small pieces, basically the small particles of it you are having, and then you dissolve it into the water. What you will be observing is that the aspirin in which you have made the powdered form of it, that is you have brought it into the smaller size particles, it will dissolve in the water at a faster rate as compared to the complete aspirin tablet when you add it to the water. So this is why you can see this thing is happening. The surface area of it has now been increased. So more number of the particles, so small particles of the aspirin, they will be interacting with the water molecules. So it will be easily dissolving into that. So this is the chemical reactivity. Also you can see generally in the preparation methods you have seen that we make use of the finely divided iron is used instead of the complete iron block as a catalyst. Suppose for a particular process iron is used as a catalyst, and on the arrow we have written like it is using the finely divided iron. Why is it so finely divided iron? Basically the powdered form of the iron you are having, because of the surface area of it now will be increased, so more reactivity of it will be there. So that is as compared to the bulk, their nanoparticles are being preferred for the reaction to take place. Okay, so this is about their third property, that is their chemical reactivity, which changes as we go from the bulk to the nanomaterials. Now moving on to the next property, that is about the melting point. Melting point we are gonna look about. So basically in the melting point you see, so what actually we are doing, we are going from the bulk to the nanomaterials. The melting point you are gonna see it will be decreasing as you are increasing the, basically we are going to the, as you are decreasing the size, the melting point it also decreases. As we go from bulk to the nanomaterials, bulk to the nanomaterials, nanomaterials, the melting point it decreases, melting point it decreases, right? So that is, we can say, with the decrease in size, the melting point it decreases. Now why is it so that this thing is happening? Again you can see the reason lies in the volume, the surface area to the volume ratio. So it is because in the nanomaterials, your surface area to the volume ratio it increases. So how is it gonna affect? So suppose this is the complete bulk material, I am heating it, so only this surface will be available that is absorbing the heat from the system to melt it, right? Whereas if you are taking the nanomaterials, now small species, so this is basically the big mid block of the species that I am having, and this is the small materials we are having. So more amount of the surface area to the volume ratio in the nanomaterials we are having. So this species will be absorbing the more amount of the heat from it, because more surface area, more amount, because this complete surface, now large number of the areas are available which can absorb the more amount of the heat. So that means to a lesser extent the heat from the outside environment will be required to melt this particular substance, whereas to melt this complete block we have to provide the more amount of the heat to melt this complete substance. So this is how the melting point is gonna vary. So we can write this thing now, that as we move from the bulk to the nanomaterials, more surface area to the volume ratio it has now increased. That is more surface area is available, to observe this, the heat, observe the energy or the heat. So that is why the melting point, it decreases. So this is the reason for that. Okay, a curve has also been observed like this, that if you make the plot of the melting point versus the particles diameter, this type of the plot it has been observed. So this constant one, it is for the bulk material you are having. This is for the bulk material. So bulk material, you can see a large diameter of it you are having, and as you decrease the size of the particle, suppose this one, the melting point is correspondingly also decreasing. And if you take in between these two, so the particle size we are decreasing, the correspondingly this melting point it is also decreasing over here, right? So this type of the plot has been observed. So this is how the melting point is gonna vary. Now moving on to the next property, that is basically the fifth property, and is gonna be of the magnetic properties. Magnetic properties. So with the help of the hysteresis loop, we talk about the magnetic properties. That is, if you have a plot like this for the magnetization, extent of the magnetization versus the applied magnetic field, applied magnetic magnetic field. So this type of the curve, it has been observed like this. So this is my hysteresis loop I am having. So this is for the bulk material, suppose it is there. Now as we are going from the bulk, and what is this basically loop it represents? This represents the loss of the energy that is there. So the loop's area, it represents the loss of the energy. Okay, so as we move from the bulk materials to the nanomaterials, now the size of the loop, it decreases. So this type of the plots you are observing like this. So as you move from the bulk to the nanomaterials, this is for the bulk. So as you have gone to the small size, so there is gonna be the smaller area of this particular loop, which represents that there is gonna be the less amount of the loss of the energy as we are going from the bulk to the nanomaterials. So in the smaller is the loop, smaller is the loop, lesser is the loss of the energy. Lesser is the loss of energy. So what is going to happen as you go from the bulk to the nanomaterials, the size of the loop is being decreased. That means the energy which was to be lost is now being decreased. So due to that, the magnetic properties, it will be improved. And in fact, what you have is you get the paramagnetism character. In fact, we call it as the super paramagnetism character. It arises when you go from the bulk to the nanomaterials. Okay, so we can say that area of the hysteresis loop, it decreases as we go from the bulk to the nanomaterials, to the nanomaterials. So we are gonna get, so as we go from the bulk to the size of this is being lost, so the less amount of the heat will be lost, and then we get the paramagnetic character, and we get the paramagnetic character paramagnetic character, or you can say we are getting is the super paramagnetism. So we can say that with the decrease in size, as the size it decreases, their magnetic movement, it is gonna increase, or the magnetic behavior, it increases. So this is how the relation is there for the magnetic properties. Now moving on to the next property, that is about the wettability, we are gonna look upon now. So the next property is called as the wettability. So what does this term wettability it refers to? So basically we have the interaction in this. So now what type of the interaction, as the name is suggesting, wettability. So something that is being wet, right? So we can say when the solid substance, it is in contact with the liquid. So this is the solid, and this liquid substance, it is being in the contact with it. So this phenomena basically refers to the wettability. So how do you define it? The phenomena that the that includes the phenomena, the ability of the water or the liquid to remain in contact with the solid substance, to remain in contact with the solid surface. So this is known as the wettability. That is basically the phenomena in which we define the ability of the liquid substance to remain in contact with the solid substance. So how do you define this wettability? This is on the basis of the contact angle. So wettability is defined, or it is measured by the contact angle, by the contact angle. So now a new term you are encountering, that is your contact angle. So first is the relationship of the wettability with the contact angle. Both of these are inversely proportional to the one another. Your wettability, it is inversely proportional to the contact angle. That means smaller is the contact angle, more is gonna be the wettability of a substance. This you can define it in the paintings that you do, that is for the coating a particular substance. You make the contact angle to be the small, so more amount of the wettability you will be having. That I'll be telling later on. Later on, firstly let us see that is about what is the contact angle we are defining over here. So this basically is the angle that is between the solid and the atmospheric, that is the vapor interface, and the solid interface. Between that, the angle that you have, this is known as your contact angle. So contact angle, basically the angle between the liquid vapor interface and the solid interface and the solid surface interface is called as the contact angle, is called as the contact angle. So how do you define this? So basically, what is basically this solid vapor interface? So suppose I am having, this is the a drop of the water, suppose I am having. So this is the drop, and in this drop there will be the presence of the liquid, and in the outside environment there is the air or the vapors are present around this air or the vapor, and the point where these two air vapor and the liquid drop, they are coming in the contact with the one another. This particular size, that is this interface, this is called as the liquid vapor interface. Liquid vapor interface, basically the outer covering of it. So you can imagine that this is a drop you are suppose having. It is not actually a drop, we can just assume it. Now this is the drop. In this there is complete water is filled in it, and in the outside environment of it there is presence of the air in this. So this liquid drop and this air, the point of the contact between these two is known as its interface. So this interface, and other is the solid substance I am taking. So the other is this solid surface I take it, solid surface interface. So this is the solid substance you are supposed having. Now this particular boundary of it, that is the interface, we can say it. Now the point of the contact, we have to talk about this. Suppose this is the surface, that is the solid surface I am having. This outer boundary, that is the solid substance, the outer boundary of it is gonna be its interface, and this this drop that we are having, in which we are having this liquid and the air, this interface, this point of the contact you have to make between these two. So let us consider a larger drop. So this is the one. So the interface of this particular solid substance and this outer layer, which was the interface of the liquid and the air interface that we were calling, the angle which is made between these two. So this tangent you can draw it, and this angle that is present between them, this theta angle, it is called as your contact angle. This is my contact angle we are having, right? So in this, based upon this contact angle wettability, it is measured. So now this contact angle, it can be your 0 degrees, it can be your 90 degrees. How you can say? Suppose this is the solid substance I am having and the liquid drop is present like this over it. So this is the liquid substance. So in this case, the angle that you are having, this is of the theta is 0 degrees you are observing. Directly in the contact, these two are there. Right. Next is, suppose you are having this particular type of the case. This is the solid and this type of the uh, drop it is present, and this is the angle that is present between these two. So this basically angle, it is less than 90 degrees. So theta will be less than 90 degrees in this case. And the third case that is possible when the solid is present and this type of the drop you are having. So the direct contact is there between these two. So the angle between these two is now is of the 90 degrees. So theta can be my 90 degrees. Also, if you see, you are having this type of the substance, the solid case, and this drop is present like this. So this is the angle between them. So this particular angle, this will be the theta angle and it is gonna be greater than the 90 degrees. So more is the angle between them, lesser is gonna be the wettability. So this is how the wettability concept it defines. So now what happens as you go from the bulk materials to the nanomaterials. So this wettability bits basically it is increasing. So with the decrease in the size, with the decrease in the size, or we can say as we go from the bulk to the nanomaterials, the wettability it increases. Wettability it increases. Basically the contact angle between the solid surface and that liquid and the air interface, it has now been decreased. That means this type of the scenario it has been observed in the first case that we are having. So with the decrease in size, wettability it increases as the contact angle it decreases. It decreases. Example, in the daily life you can correlate this, that is the coating of any substance if you have to do it. So that coating material that we are applying, it is basically the nanomaterials you are having, and you can see that only a thin layer of it is sufficient enough to do the coating of this, not the thick layer you have to impose over it. Just a small amount of the layer is sufficient enough. Reason being, the nanomaterials that I am having, so that is the basically the liquid and the air interface it is present, and on that solid substance the coating of it you have to do it. So the nanoparticles, their contact angle between this and that particular, the contact angle is now being on a decrease. So a wettability it will increase. So only a small amount of the substance it will be sufficient enough to do the coating of it. So a thin layer is sufficient enough to do the coating. So this is the reason for that, and why is that, this is the reason, and you can see why in the coating materials the nanoparticles are preferred over the bulk material. So a thin layer is sufficient enough because the wettability it will be increasing in that case. So this is in the daily life example you can correlate it. And with this we are done with the properties of the nanomaterials. We have seen about their electrical properties, their optical properties, melting point, their that was magnetic properties that is defined on the basis of hysteresis loop. We have seen about the wettability, and one more property we have seen, that was about their chemical reactivity, that is for a particular reaction if you want to do it. So instead of the complete block of it, a small particles are preferred because of the surface area to the volume ratio it is increased and the reactivity it is increasing. So this is it about the properties of the nanomaterials, right? So now we are gonna move upon to the next topic, that is about the nanomaterial structures we are gonna look about. So we are gonna look about the nanomaterials, nanomaterials structures we are gonna look. That is how do these actually look. what is gonna be the actual structure of this. So we have seen that we can classify the molecules as your, on the basis of dimensions. You can have the 0 dimensions, you can have the 1 dimension and the 2 dimension. So based upon that, three of the materials generally we are classifying it, that is your quantum dots, you have it, quantum dots, you have it, you have the quantum wires, quantum wires, and we can have, next is we are having is the quantum walls. So this is basically gonna be the general structure of these nanomaterials. In these three categories you can classify it. So your quantum walls, firstly that you have it, it falls in the category of your basically the one dimension. Just a second. So basically this is the quantum wells, not the quantum walls. So A is not there, it is the wells. Okay. So the quantum wells, basically in this quantum wells, your one dimension is lying in the nanoscale region, rest two are the normal ones. So in the quantum wells, we have only one dimension, only one dimension is in the nanoscale region, is in the nanoscale range we are gonna have it. Next is, if you talk about the quantum wires, in this two of the dimensions are in the nanoscale, two dimensions are in the nanoscale range we are having, and rest one is in the normal range you will be having. Whereas in the quantum dots, you will be observing all the three dimensions are lying in the nanoscale region. All the three dimensions, all the three dimensions are in the nanoscale range. So if all the three dimensions are lying in the nanoscale range, we call this as the zero dimensional nanoparticles. If your one of the dimension, if basically one dimension is not excluded and two are there, so this is comes your one dimensional nanoparticles. And if only one of the dimension is in the nanoscale and two are not there, so this becomes my two dimensional nanoparticles. So zero dimensional, one dimensional, two dimensional, broadly we can call them as the quantum wells. It is my two dimensional quantum wires. This is my one dimensional, and the quantum dots zero dimensional. Now what we are going to do is we are going to look upon to the structures of this, that how you can actually, how they are going to look to us. Okay, so we are starting is with the bulk material. Suppose this is the cube I am considering. This is the one. This is the one. In this you can consider this cube, or the better is to consider it the cuboid you are having. So this is gonna be the length of this cuboid. This is the length, this is the length and the length. And this particular thing is the breadth of it. And the third is the height of it we are having. So this is in the bulk case you are having that none of these three, your length, breadth or the height is lying in the nanoscale range. That is, you are not having it into the range of the this 1 to the 100 nanometer range. This is not lying. So now what I do is I try to bring one of this dimensions into the nanoscale range. So we try to bring one dimension in the nanoscale range, in the nanoscale range. So what is gonna do, what we are gonna how we are gonna do this? One dimension, basically we will be trying to bring this a length falling in the one dimensional range. Basically not the one dimensional, it is lying in the nanoscale range. So length we are trying to bring it into the nanoscale. So this is gonna look like this. This length we are decreasing, the breadth is gonna remain the same, this breadth will be also remaining the same, and this height is also gonna remain the same over here. So you will be having this type of the structure. Let me draw this again. So this type of the 3D structure you will be observing. Right, so you can see here in this, what we have done is this length we have brought it into the nanoscale range. This breadth, it is remaining the same, and this height also you can see that You can just say that it is the same only. So length is brought into the nanoscale range. Length is in the nanoscale range. So if one of the dimension is in the nanoscale range, what type of the species we call it? In the one dimension, it becomes your quantum wells we are having. So this is basically the structure of my quantum wells I am having. Quantum well it is called. Now if you try to bring the breadth of it also to lie in the nanoscale range, so how is gonna be the structure look now? So this is the length we have brought it like this. The height we have to keep it to be the same only, that is in the bulk region we are lying it. And let me draw this again. So length and this breadth also we have now decreased. So this is gonna be the structure and this is gonna be the height of it. So this is basically a three-dimensional structure you are having. I think that it is not clearly visible. Let me draw this again. So this is basically and actually it is the three-dimensional, so it becomes a bit difficult to draw it. So this type of the scenario it is there. So yeah, right now it is correct. So this becomes my quantum wires now. So this is known as the quantum wires. So this is, you can see now here the length and the breadth we have brought it to be in the one dimension, and this height that is present, it is lying in the normal scale range, and the length and breadth are lying in the nanoscale range. So this is how the quantum wires are gonna look. Okay, and further if you make the third dimension also to be lying in the nanoscale range, so this time you will be getting is like this species. So this is gonna be the cube that you will be having. So a smaller cube you can see, and in this the length, this is the breadth, and this height. All of this three we have brought it into the nanoscale range, and this becomes my quantum dots. This is my quantum dots we are having, right? So in this quantum dots. So here all the three dimensions, all the three dimensions are in the nano range, range. And as we have shifted from the bulk to the quantum, so why is it basically the name is quantum wires, quantum dots, quantum well? Why is it so? Because we are shifting from the bulk to the discrete energy level. So as we shift from the bulk, in this you were having the band gaps, you were having the bands, and in the next, that is to the nanoparticles, if you are seeing the nanoparticles when we are observing, and there we have the presence of the discrete energy levels, and that thing we study in the terms of the quantum, right? So basically from the bulk, that is the classical, you can say, we are shifting to the quantum. So that is why the name it is called as your quantum dots, you call it, or the quantum wells, or the quantum wires it is. So this is basically the general structure of your quantum dots, that is your 0 dimensional, 1 dimensional, and the 2 dimensional, and this is how you can draw them. Okay, now we are gonna see is how you can do the preparation of these. So we will be now looking upon to the, so now we are gonna look upon to the preparation of these bulk materials, from the bulk these nanomaterials. So basically you can see we from the bulk materials we prepared these quantum wells, and from the quantum wells you can prepare your quantum dots. So this name of the process is, so from the quantum wells we can prepare the quantum dots, and for this the process that is used, this is known as your lithography. So this particular process is used, the name only you can remember, the exact mechanism it is not important for us. So basically in the quantum wells you can prep from that the quantum dots, in which all the three dimensions will be lying in the nanoscale range. Okay, so quantum dots it can be prepared. This is the name of the process we are gonna see. Okay, so now next is we are gonna see is the approaches that are used for the preparation of these nanomaterials. So far what we have done is we have looked upon to the basic portion that what species we call the net to be the nanomaterials. Then we have seen about the properties of it, that how do these properties are gonna vary from the bulk materials. We have looked upon to the structures of it, that how do these HLEs are gonna look. Now we are gonna see is the preparation of it, that is different approaches are used to prepare my nanomaterials that we are gonna look. So approaches to prepare the nanomaterials, to prepare the nanomaterials. So broadly, two of the approaches are there, that is known as the top-down approach, top-down approach, and other is called as the bottom-up approach, top-down and the bottom-up approach. So basically we have seen this thing, that when you have the atoms or the molecules, right, this is the smallest existing matter that we have in the nature. When you take the combination of this, so clusters will be formed, right, and from the clusters we can prepare the nanoparticles, nano, or we can say that these clusters only are my from the atoms or the molecules. When you combine this, you get the nanoparticles. So basically, let us start it with the bulk materials, and from that the nanomaterials we will be preparing. So first is you have the bulk materials, and you break it into the smaller particles, that is called as the microparticles you are having, and then you go to the nanoparticles, and then the further if you bake it, you will be getting the small clusters of it, that is basically the molecular species quite larger than that, and the smaller ones we are gonna get as the atoms or the molecular species we are gonna get, right. So this is the thing. So as you go from the bulk, we have to go to the nanoparticles, right. So we can go either from the bulk to the nanoparticles, or we can go from the atoms molecules to the bulk particles. So two of these methods are there. So when basically you go start with the bulk materials and you break this particular species and go to the nanomaterials, so you are starting is from the top. So this particular side, that will when that means when you are starting with the bulk material and going to the nanomaterials, this is called as your top down approach. Whereas if you do the atoms and the molecules small combination and make your nanoparticles, this is called as the bottom up approach, bottom up approach, bottom up approach. So basically in the top down approach, what we do is we take the bulk material, and you go to the nanoparticles. So how do we do this? The bulk material is broken down into the smaller species till we get into the nanoscale range. So we do is breaking down of the bulk material to the nanoparticles. This is called as your top down approach. So basically we are starting is from the top, that is the larger molecule you are starting, and breaking it into the smaller species. So like this you can say that this is the complete larger molecule you are having, this is the bulk species you are having, right, and you break it. So you will be getting this type of the species, like this small particles you are having, right, and then further you do the breaking of it, you will be reaching it to the nanoparticles, right. So during this process what we are doing is breaking the larger one to the smaller one we are going, and during this process a large amount of the waste is being produced, and that is the biggest disadvantage of the top to the bottom approach. So you can see from the bulk one, so this is the bulk material I am taking. I want to go into the nanoscale region. What I'll be doing it, I'll be breaking it into the smaller species. So till I reach to the smaller species, a lot of the material it will get wasted in this, right? So this is the biggest disadvantage of the top down approach. So limitation of the top down approach is a lot of the waste is being produced. A lot of waste is produced. Lot of waste is produced. Also you can see that in visualization it will be seen that the particles that I am getting, they are having the uniform structure. That means no deformities are present in it. But in actual, the structure actually these are having the large amount of the deformities when you are following the top down approach. So you can say is that there will be the irregularities, or we can say some of the deformities in the structure can arise. In the structure it arises, right? So the nanoscales, they are not having the uniform structure. So to now rectify this, we have used the other approach, that is the bottom up approach we are using. That means we start with the small particles and then we go to the nanoparticles. So here we take the small particles are combined to form the larger particles, large particles large particles that lie in the nanoscale range. So here you have prepared from the bulk, you were going to the smaller particles. Now you start as with these even smaller particles, that is your atoms or the molecules you take it. Then you do is the combination of these particles I am having. So this type of the species we will be getting. So these are known as the clusters of it. These are the clusters of the atoms we have got it. Now further if you go, so they will be reaching up to the nanoscale particles like this. So this is gonna be the nanoscale particles we are getting. So big clusters basically that lies in the nanoscale range we are getting. So this is the nano particles we have got it. So this is known as the uh, this was the top down approach, top down approach, and this is called as your bottom up approach. Bottom up approach. So start is from the bottom, that is the smallest level, and go to the higher level. So these are the two of the approaches that are basically used to prepare your nanomaterials. You can use the top down approach, basically breaking the bulky materials to the nanoscale, and the bottom up approach, basically combining the atoms to the reaching up to the nanoparticles. So the disadvantages of the top down approach, it was to remove it was that a lot of the waste was being produced and irregularities we were having, and these deformities it was removed in the bottom up approach. That means no wastage you are gonna get, because atoms they will be combining to form the particles, and deformities will be also reduced in the nanoparticles. So this is how we can prepare the nanoparticles. So now we have seen how I can prepare my nanoparticles, what approaches can be used. We have seen its properties. Now we are gonna see that suppose if a chemical reaction I have carried it out and expected that the formation of the nanoparticles will be there. So how can I characterize it? That means what basically techniques I'm gonna use to detect the nanomaterials. That is to look what is the structure of these nanoparticles, what is its crystallographic structure, what is its surface morphology it is carrying, what is its inner structure. So for that various techniques are being used. So now which technique is gonna tell us about the nanomaterials, which property, that we are gonna look upon now. So that is about its characterization. That means various characteristic properties of the nanomaterials that you are gonna observe. So the that is the technique that we use. It is called as the SEM, which is basically your scanning electron microscope. So this is basically my scanning electron microscope. So the scanning electron microscope, suppose for an example, let us try to correlate about the nanomaterials. So the recent use of these nanoparticles, you have seen it in the coronavirus detection when you were having. Right, so the structure of the coronavirus, it was like this circular species, it was there, and it was carrying these spikes like this, it was present over here. So how do I came to know that these spikes are present over it, and sometimes something like this, the structure of the coronavirus it looks, that is using these techniques only we have identified it. The scanning electron microscope that is basically used, it scans the nanoparticles from the outside surface. That means we get to know about the surface morphology. So that is the outer surface of it, it is getting being scanned using the scanning electron microscope. So we get as the surface morphology. Surface morphology. That means only the outer structure of the uh, nanoparticles we can get to know using the scanning electron microscope. Next is about the TEM. Now TEM, it stands for your transmission electron microscope. So this is transmission electron microscope. So using the transmission electron microscope, you can tell about the internal structure of the nanoparticles. So using this, we can tell the internal structure of the nanoparticles. Nanoparticles. So how these techniques are basically working, in the details I'll be discussing in the next class, but for the while, just an overview. The scanning means the outside structure of the nanomaterials. If you want to see, you use the scanning electron microscope. You want to see internally that how the structure is gonna look, that is used in that basically we use as the transmission electron microscope. Next is the AFM. AFM stands for your atomic force microscopy. This is atomic force microscopy. And using this you can tell the surface topology. Basically, if the surface of the, you can tell that if the surface that of the nanomaterial that I am having, it is a smooth surface or it is the rough surface it is having. So that is basically studied under the AFM technique. So we will be looking upon here, you will be getting to know about the surface topology. And that too about the surface roughness we are gonna talk. Surface roughness, it can tell that if I'm having the smooth surface of the nanomaterial, it is there, or it is the rough surface, that we can study using the atomic force microscopy. Next is about the X-ray diffraction. So using the X-ray diffraction, I can tell about the crystallographic structure of the nanoparticles. So we can tell about the crystallographic structures of the nanoparticles So this thing you can tell. Crystallographic structure basically refers to that suppose a solid substance I'm having. I want to tell about its lattice points, its dimensions, that is what is gonna be the length of it. So basically in a unit cell, the characteristics that we define, that is called as the lattice parameters. what is the distance between the neighboring particles, distance between the planes that I'm having. So all that things we get to know using the this X-ray diffraction technique, which is gonna tell me about the crystallographic structure of the nanoparticles, right? Now the next technique that we can use for the characterization of the nanoparticles, this is the FTIR. So generally this FTIR is basically, you have learned it in your IR spectroscopy. In that detection you might have encountered this term, that is my FTIR. So what was my IR spectroscopy telling me? That what type of the functional groups are present in the particular molecule, right? So FTIR basically is gonna tell in the nanomaterials what type of the chemical bonds are present in it. So FTIR is gonna tell us about the chemical bonds, and also it tells us about the molecular structure of it. The molecular structure of it. Right? Next is using the Raman spectroscopy. So using the Raman spectroscopy, you can tell about the vibrational bonds present in the nanomaterials. So this will be used to tell the vibrational modes and their chemical composition that we are having. Chemical composition. Next is about the UV visible spectroscopy. So about the optical properties, that is what is going to be the color of this particular nanomaterials. Basically the electronic transitions are studied using the UV visible spectroscopy. So here using that, what you can tell is about the optical properties of the particular nanomaterial we can tell. So using the UV visible, you can tell about their optical properties and about the band gap also, and the band gap, because corresponding to the band gap also only the light is being observed by the molecules. So we can get to know that if particular species is gonna be suppose red in the color, so complementary color would have been absorbed by this. So from that you can get to an idea that what is the band gap of this particular species, right? Next technique we can use is, that is the TGA. TGA stands for your thermogravimetric analysis. Thermogravimetric gravimetric analysis. This technique basically tells us about the thermal stability of a particular species. So what you do is, in the TGA, you heat the molecules to a particular temperature, and if you see that if that particular species can withstand a particular range of temperature, that means we can get to know about the thermal stability of the particular species. So for the nanoparticles, if I want to know that if my nanoparticle material is to what temperature it is gonna be my thermally stable, so that is studied under the thermogravimetric analysis. So this basically is telling me about the thermal stability, thermal stability of the molecules, right? Thermal stability. This is not visible. Thermal stability of the species we are gonna look. Next property, that means the technique that you can use is the zeta potential measurement. That means it can tell me that if my species is the charged species or not, just like in the colloid substances we have. So here when the two of the opposite charges layer that you have, so there exists a potential between these two opposite charges that is called as the zeta potential. So by measuring the zeta potential, you can measure the charge over your nanoparticles. So we can get to know about the surface charges, and about the colloidal stability of it. Colloidal stability of it. Okay. Next technique is your XPX. XPS stands for your X-ray photoelectron spectroscopy. Photoelectron spectroscopy. So using this, you can tell about the surface chemical composition that you have. Surface chemical composition. Basically, what type of the chemicals are present upon the surface, that you can get to know using this technique, and also about the states of it. So these are the various techniques that you can make use to characterize the nanoparticles. That is, suppose the reaction I have carried it out in the lab and I want to find it out that if my nanoparticle it has been formed, then using that what is gonna be the structure of it. So all these different techniques we can use it. So now in the great detail we have to learn is about the SEM technique, that is your scanning electron microscope. How is it being used to find the nanomaterial structures? We have to look upon to the TEM, that is a transmission electron microscope. We will be learning about the AFM, that is about the atomic force microscopy, and the X-ray diffraction. So all of these four techniques we will be learning in the great details. And along with that, one more is there, that is the STM, along with the AFM only, that we will be discussing. So that is it with the characterization, the techniques that you can make use, how the working of it is gonna be done, that in the next class we will be starting it. So far what we have learned is, that is how the what are the basically nanomaterials, how do they differ from the bulk materials, how do their properties it varies from the bulk materials, how you can prepare it, the different approaches that you can make use, what is the structure of these nanomaterials, and what are its characterization. So that is it with this class now. So in this class, all the topics that I have told, basically this characterization of the nanomaterials, the various techniques that are there, direct question will be framed from this. You will be getting is the technique name, and in the form of the match the column, these questions can be framed, that which particular technique is used for this, for studying the basically what characteristic property of the nanomaterial is shown by which of these techniques. So like this the questions will be framed, and also about the some of the theoretical questions that we have discussed. So all that things we just keep in mind. Okay, so that is it for this one now. Now the next class, as I said, all these 4 to 5 techniques that we are having, how do the working of this is gonna take place, that is useful for the determination of the nanoparticles characterization, that we will be looking upon in the next class now. So that is it for this one now.